Hallelujah, praise the Lord who's given us another beautiful day to do physics. A bucket of water is whirled in a vertical circle of 75 centimeters. That's the radius of the circle. What is the minimum speed that will keep the water from falling out?
God's
help. You can do physics. Boss, as you are created.
You are created in God's image.
To be fruitful and multiply.
Fill the earth and subdue.
Okay, so we draw our circle that the bucket's spinning around in. The speed of the bucket or the instantaneous velocity is unknown. We went ahead and put a coordinate system up there. And it's convenient to draw the picture with the bucket at the top because our intuition suggests that when the bucket's at the top, that's the most likely instant for the water to fall out. So if we can keep the water in the bucket at the top, then we're keeping the water in the bucket. Okay, so the general principles that we're working with here, one is centripetal acceleration. And the other one is Newton's second law. All right, now let me just clarify our terminology here. We're going to be talking a little bit about centripetal acceleration and centripetal force as we work through these problems. And centripetal acceleration is simply the acceleration an object has when it's moving in a circle. Centripetal force is simply the force you need to keep you moving in a circle. So don't confuse it. Some people talk about centrifugal this, centrifugal that. We're not talking about centrifugal anything in this problem. We're talking about centripetal. All right, now to develop.
God has crowned you with glory and honor.
Honor to rule over his creation.
Our
bullet point plan. We're gonna go ahead. We're not told the mass of the water, right? So one of the things you might have learned by now in your intro physics course is that if you're not given the mass and you're not asked for the mass, just set it equal to Bm. And odds are pretty good it's going to cancel out somewhere along the way. We're going to express the centripetal acceleration in terms of V and R. We're going to express now the centripetal force in terms of centripetal acceleration and mass. So that ends up giving you, once you check all these boxes, you end up with the centripetal force in terms of M, B, and R. Now let's go ahead, we get some ideas straight here in the development stage. The centripetal force, that's the force needed to move in a circle. Now, the force you need to create some kind of motion is different from what physically is applying that force. For example, some things that could physically apply a force could be friction, tension in a string, some other push or pull, gravity, magnetics, electrostatic forces. Those are forces that you might actually have, but the centripetal force is a force you need. Some other force needs to supply it. So as this bucket's moving in the circle, there are two places where this centripetal force might come from. The bucket is on a string of some kind as we're spinning it around, and at the top there's also the force of gravity. Now, one of the things that we think about by intuition here is that at the top of the circle, well, the string's not really touching the water anyway. The string's touching maybe the handle of the bucket. What's touching the water is the bottom of the bucket exerting a normal force, and that gets sort of translated through the bucket from the string to the bottom of the bucket. All right, so but at the top of the circle, the bottom of the bucket's not exerting any force on the water in this minimal velocity scenario, right? That water's almost going to fall out. So the force that we have is the force of gravity. Alright, now, often is the case in these centripetal force problems, we'll set the force we need equal to the force that we have, and then solve for the unknown in this question, in this case, which is that minimal velocity.
Science is a gift from God,
To help us master nature,
but sin added thorns and thistles.
requiring the sweat of your brow to succeed. Alright, so to evaluate here, let's go ahead. The centripetal acceleration is equal to negative v squared over r. Now the centripetal force. If we're going to create this acceleration to move in that circle, that's Newton's second law. It's mass times acceleration, so it's simply negative mv squared over r. Now we go ahead, set Fc equal to Fg. So this is negative mv squared over r. Well, at the top of that circle, what's the force of gravity on the water? It's negative mg. Alright, so now we're just to this stage here where we're solving for v, multiply through by negative 1, cancel out the mass as we thought it would, multiply both sides by r. So now the velocity is the square root.
Learning physics
Often requires prayer
as we submit
to Jesus Christ
as risen.
as risen King of Kings and Lord of Lords, RG. Alright, so now we can go ahead and plug in our numbers here. So it's the square root of 0.75 meters times 9.8 meters per second squared. Alright, now you can do the math on the numbers, and that's pretty simple, and that turns out to be 2.711. Now let's think about the units. Meters times meters per second squared is meters squared per second squared. And then you apply the square root operator. The square root of meter squared is meters. The square root of second squared is seconds, so it's meters per second, which is what we were expecting. Alright, so now to assess.
We reign by surrender.
We reign by surrendering to Jesus and praying for our daily bread, which includes success
Success in our schoolwork.
God will answer and lighten our yoke and the impact of the thorns and thistles in our labor. Are our units right? Yes, we took due care on the units. We did the math on the units. We were expecting units of velocity. We got our units of velocity. What about the sign? We didn't pay a whole lot of attention to the signs here because the direction that you spin it doesn't matter. Right at that top, the centripetal acceleration is down, and so the signs, there's no problem with the sign. What about the magnitude? Now let's think about this, because let's ask ourselves about how fast is that really, this 2.7 and change meters per second. So let's think about the circumference of that circle. The circumference of that circle is 2 pi r. So you just plug that in, and so that's 2.3. I may have made a calculation error here. I'm going to go ahead to the calculator, double check this. So 2 times pi times 0.75. Yes, I did make a little bit of a calculation there. So it's 4.71 meters is the distance around that circle. So swinging that bucket around, it's going to take it about 2 seconds for that bucket to go around that circle. And then I've done this before and I've got some intuition with it. But in reality, it doesn't even matter that there's water in the bucket, right? It's how fast you need to spin any object around that circle so that it barely stays in a circle at the top, right? So you kind of sense at the top it wants to stop going around the circle and just fall, right? Just let it be the water falling out of the bucket. So swinging something around a circle of that radius once every 2 seconds, give or take, maybe a little faster than that, a second and a half, get a little margin for error. That'll work. So that makes the magnitude assessment work out for us as well.
Written in the Word, in the good, good Word is a message from our God. Gonna tell you all about how to get to the kingdom, the good life. Written in the Word, in the good, good Word is a message from our God. Gonna tell you all about how to get to the kingdom, the good life. Oh, I love Jesus.